Another application of Hess's law is the use of bond dissociation energies to calculate the change in enthalpy for a reaction. All right, let's talk about bond dissociation energy. Bond dissociation energy is the amount of energy that must be supplied to break a chemical bond in an isolated molecule in the gaseous state. So the bond dissociation energy is the energy required to break a bond. For example, if I have water molecule and the hydrogen and the oxygen want to break up, the amount of energy it would take to break that bond is the bond dissociation energy. This is going at things backwards compared to energy of formation. Why do I say it's backwards compared to the enthalpy of formation? When the bonds are formed, energy is released. When we break bonds, it requires an input of energy. If you think about it, that makes sense. When you break up with somebody, it takes a lot of energy, right? You break up with them, you're depressed, you sleep for days, you crave sweets and all the calories you can get a hold of, and it's just such a trying process. So it requires a lot of energy. Therefore, it makes sense that bond dissociation energy is going to require an input of energy. The energy required to break a bond is equal to the energy released when the bond is formed. So the dissociation energy is equal to the energy released when a bond is formed, equal in magnitude, opposite in sign. Dissociating a bond is an endothermic process. Forming a bond is an exothermic one, which again, we understand. What happens when you first fall in love with somebody and first form that bond with them? Oh, you're so excited. You can't sleep. Energy flows from them as long as you spend every single moment in their presence, right? So we know that forming a new bond provides energy, breaking one requires it. There is a relationship, is the way I would phrase it, between the standard enthalpy change for a reaction and the bond breaking reactions. However, there's a couple significant differences on how we're going to use these bond dissociation energies compared to how we were able to use our enthalpies of formations. One thing I really want you to note when you're looking at this table is the sign of all these bond dissociation energies. All these bond dissociation energies are positive. And if they're all positive, what does that mean? It means the process of breaking a bond is endothermic. In order to break a bond, it requires energy. But we knew that already, right? Because breaking up is hard to do, right? You've ever ended a relationship, what happens? You're tired, all your energy's used up. You spend hours crying. You wear out your friends, right? Breaking up requires energy. It's hard to do. What about those enthalpies of formations we saw? In enthalpies of formations, where we were forming compounds, sure, some of them were endothermic, but a lot of them were exothermic. And our enthalpy of formations where we were forming bonds, you saw a lot were exothermic. But here when we're breaking them up, it requires energy to break up, right? But when we're forming something, it's exothermic. It gives off energy, right? It's like finding a new love to bond with, right? You fall in love and you got that extra energy. You're up all hours of the night holding hands and talking and again wearing out your friends. Why am I even friends with some of these people? But at any rate, I digress. The point is that breaking a bond is an endothermic process. Forming one is an exothermic process, and that's going to have big ramifications on how we handle things mathematically. Because the enthalpies of formations were exothermic, when we solved for our reaction, what were we doing? Let's take a look at a simple reaction real quickly here. Let's look at the simple reaction of the formation of water. From a perspective of the enthalpy of formation, what are we doing? We're forming water, right? So our end state has to do with formation. It's written how these values are calculated, right? We're forming product. So it makes sense that when we work our Hess's law, we're taking the enthalpy of formation of our products and subtracting the enthalpy of formation of our reactants. Why? Because are we forming these guys? No! We're breaking them up, right? We're doing the opposite of what the enthalpy of formation was designed to measure. And mathematically, the opposite is subtraction. So you can understand why we're subtracting the reactants and the products from the products. However, what about from the perspective of bond dissociation energies? From the perspective of bond dissociation energies, we're breaking in our reaction. In order to carry out the formation of water, we have to break these hydrogen-hydrogen bonds. We have to break these oxygen-oxygen bonds. These values are the energy it takes to break the bonds, right? Yes? So the reactant side, what occurs on the reactant side for bond dissociation energy matches how the quantity in the tables are measured. So mathematically, our reactant side for bond dissociation energy is following the trend. On the product side, however, what's happening? Are we breaking oxygen-hydrogen bonds on the product side? No, we're forming them. We're doing the opposite of what the table's for, right? The table measures the energy it takes to break something. In our reaction, we're forming it. So mathematically, all these quantities have to be the opposite. So that's why, for bond dissociation energies, we subtract the products. I'll repeat all this again on the next slide. All right. We can treat our bond dissociation energies just like our enthalpies of formation and use them to estimate the change in enthalpy for a given reaction. Now, these are a little bit trickier because we're actually going to have to, in some examples, draw the Lewis structure of a molecule and count up the actual number of bonds being broken. But for this reaction, it's simple enough. Another danger of doing this comes in from the formula. If you look at it, is dissociation of the reactants minus the dissociation of the product. In other words, that's right. Danger, Will Robinson, danger. Why is this formula dangerous? Because it's the exact opposite of how it is for your enthalpies of formation. Remember, for enthalpies of formation, it's products minus reactants. But for dissociation energy, it's reactants minus products. But if you think about it, we're going the opposite direction, so it makes sense. After all, when we were dealing with enthalpies of formation, we were dealing with the energy change for forming bonds. With our dissociation energy, we're dealing with the energy required to break them. So it makes complete sense that they would be the opposite way. After all, in a reaction, what are you doing? You're forming product bonds. And you're breaking reactant bonds. If the dissociation energy is the energy required to break a bond, then the energy to form a bond would be the mathematical opposite of the dissociation energy. So that would be why we would be subtracting products and adding our reactants. So be aware of that crucial difference, and you have to keep them straight on exams. If you've got questions about that, please ask. All right, so let's actually work the example. The first thing you have to do when you work these problems is you have to actually draw the Lewis structures of the compounds if they're not drawn for you. In this case, our Lewis structures are about as simple as you can get. Next, look up the values of those bond dissociation energies. I'm breaking a hydrogen-hydrogen bond, and that has a bond dissociation energy of 436 kilojoules. My chlorine-chlorine, and make sure you do chlorine-chlorine and not carbon-carbon, is 243. My hydrogen-chlorine bond is somewhere on this. There it is, 432. And where are these numbers coming from? They're coming from the table I just showed you, which you, of course, printed out to take notes on. Okay. So I'm breaking one hydrogen-hydrogen bond. I'm breaking one chlorine-chlorine bond, requiring the input of energy. Then I'm going to form two hydrogen chloride bonds, which releases energy. Hence the negative sign. I take all of that, I plug it into my calculator, and I get a negative 185 kilojoules per mole. Use the bond dissociation energies to estimate the change in enthalpy for the reaction of methane with fluorine according to the equation shown. All right, the change in enthalpy, whoops, wrong tool. The change in enthalpy for our reaction is equal to the sum of the bond dissociation energy of the reactants minus the sum of the bond dissociation energy of the products. We don't have to go running for a chart since they were nice enough to give them to us here. What we do need to do is we do need to draw a couple Lewis structures to help us with this task. I'm going to draw the entire reaction as a Lewis structure. I have methane reacting with two fluorines, and I'm leaving out my lone pairs of electrons since we're wanting to focus on the bonds. So that's what the Lewis structures of these compounds look like. Why is it important? It's important to draw the Lewis structures so that you can know the number of bonds. Because without these Lewis structures, you'd be tempted to look at methane and say, hey, I've got one carbon-hydrogen bond there. Do you have one carbon-hydrogen bond in methane? No. Look at methane. How many carbon-hydrogen bonds do you have? You have 1, 2, 3, 4. You have four carbon-hydrogen bonds that you have to break. So you have to account for that in your dissociation energy. So I have 4 carbon-hydrogen bonds I have to break. And I have 2 fluorine-fluorine bonds I have to break, right? I have 2 molecules of fluoride, and they each have 1 bond. So I have 2 fluoride-fluoride bonds at 159. Minus the sum of the dissociation energy of our products. We look at our products, and once again we see there was a potential to be fooled. Because if we look here, it looks like there's 1 carbon-fluoride bond. In reality, there's 1, 2, 3, 4. 1, 2, 3, 4 carbon-fluoride bonds at 450 each. Plus 2 hydrogen-hydrogen bonds, right? Hydrogen-hydrogen is, the molecule has 1 bond and we have 2 molecules. So 2 hydrogen-hydrogen bonds at 436 each. Close parentheses. Whoops. Oh no. And magic! I love that. The screen suddenly changed for you guys. Alright, I moved it down here so it looked a little bit neater, so we can do our math. And inside our first parentheses we have 1,958 kilojoules minus 2,672 kilojoules gives us negative 714 kilojoules, which happens to be answer A. Chemistry is easy, life is hard.
Fantasy web.
Alright, one more example. Given the bond dissociation of the energies shown, estimate the heat of reaction for the reaction below. We're going to be using our standard formula of the change in enthalpy for the reaction is going to be very close to the sum of the dissociation energy of the reactants minus the sum of the dissociation energies of the products. So, we have to start by calculating them. They've given us the information in somewhat an unusual form this time. They've given it to us graphically, using some balls and stick models. How great is it that we're in a field where we get to play with Tinker Toys? But at any rate, speaking of which, there's nothing great like a really great villain, and I've forgotten keywords, so why don't you write down Deathstroke the Terminator. Deathstroke the Terminator. Deathstroke the Terminator. Alright, once you've written down Deathstroke the Terminator, let's take a look at figuring out the dissociation energies associated with each molecule. Let's start with ethanol here. Ethanol is represented by this model here. How did we know this was ethanol? Well, it's the biggest molecule, and therefore it's going to have the biggest model is one way. The other way would be, hopefully, by this point in chemistry, you're used to seeing these models. You're also, hopefully, have begun to develop some sense of the convention. And there is a convention in chemistry that when we use the ball and stick models, we represent carbon with black balls. And we represent hydrogen with white balls. And we represent oxygen with red balls. That's convention for ball and stick and physical models. Alright, so now we've identified what elements the balls represent. Now we need to calculate the dissociation energy for our ethanol. You have to be very, very careful with your accounting when you're doing this. When we look at our ethanol here, in this molecule of ethanol, how many hydrogen-carbon bonds do we have? We have 1 here, 2 here, 3 here, 4, 5. 1, 2, 3, 4, 5. So I have 5 hydrogen-carbon bonds. Each of those has a dissociation energy of 413 kilojoules. Our next bond we want to look at is our carbon-carbon bond. We only have 1 carbon-carbon bond in the molecule. So that's 348 kilojoules. Then we have a carbon-oxygen bond. We only have 1 carbon-oxygen bond. And according to our little diagram, it has a bond dissociation of 360 kilojoules. Then we have an oxygen-hydrogen bond right here, and we only have 1 of them. For a total of 463 kilojoules. So the sum of the bond dissociation energies for our methanol take our calculators, put all of that in, and I wind up with 3,236 kilojoules. So that's the bond dissociation for our methanol. Now, if we look at our chemical reaction, we need to do the same thing for our oxygen. They've made that pretty easy. Our oxygen has one double bond, and that double bond has a value of 498. And this is a question I commonly get. I've got two bonds here, right? So is this 498 kilojoules for each one of those two bonds, or is it for breaking both of them? It's for severing both of them. So each oxygen molecule would have a total bond dissociation energy of 498. All right. So we go back to our tally sheet here. The sum for our reactants is going to be the 3,236 kilojoules from our 1 mole of ethanol, plus we have 3 molecules of oxygen. 3 moles of oxygen, and each mole of oxygen has a dissociation of 498 kilojoules. So now we have to do the dissociation energy of the products. The first thing we're going to look at is our carbon dioxide here. This molecule is our carbon dioxide because we have our red oxygens connected to our black carbon. They're connected to the carbon by a double bond, and that double bond has a dissociation energy of 804 kilojoules. There are 2 double bonds here, right? So if I was to do carbon dioxide, I would say I have 2 of those double bonds at a value of 804 each, or a total of 16,008 kilojoules for each molecule of carbon dioxide, because I have 2 double bonds, each at 804. So now I've got my dissociation energy for carbon dioxide. The hard one, or I think the tricky part of this problem, and one of the reasons I went ahead and did it, was oxygen. Not oxygen, water. Do we see a water molecule anywhere here? No. Why didn't they give us a water molecule? Here's the reason they didn't give us a water molecule. Because they gave us all the information we needed for our water molecule. A water molecule forgive my crude artwork there. A water molecule consists of an oxygen attached by single bonds to 2 hydrogens. So we only have 2 bonds we have to worry about, and both of them are the same. Do we already have a dissociation energy for a hydrogen-oxygen bond? Yeah, they gave it to us right here. Because here we have an oxygen Here we have an oxygen attached to a hydrogen, and we know it has a dissociation energy of 463. So they gave us, by telling us this piece of information, the dissociation energy for water. So we've got two hydrogen-oxygen bonds with 463 kilojoules each. So if we go to our tally sheet for water, water has two hydrogen-oxygen bonds at 463 each. That gives us a dissociation energy of water of 926 kilojoules. So now we have our dissociation energy for water and our dissociation energy for carbon dioxide. So now we're going to come down here and plug them into our sum of our product. In my chemical equation, I have 2 molecules of carbon dioxide. So 2 times the dissociation energy of our carbon dioxide moles of carbon dioxide, dissociation energy for carbon dioxide. Dissociation energy for carbon dioxide. Plus our dissociation for water. If we look at our equation, we have 3 molecules of water. And each one of those waters has a dissociation of 926 kilojoules. So now it's plug and chug. Okay. And I get 4,730 kilojoules per mole. And I made a mistake when I was writing it. I wrote a plus sign there. It should be a minus sign. Minus the sum from our products, and that's 5,994 kilojoules per mole. For a negative 1,000 and that's it. Oh, let's make sure I'm right. That's always good. Yeah, there it is. And that's it, and that's about as hard as we can make the dissociation energy problems. Beep.